Swayam Prabha. Digital India. Educated India.
Okay, so now we learn the regular wave, right? And in the ocean is not regular wave, it's not one frequency. So to understand that, we have to talk about the random sea and the power spectrum. And so power spectrum, this was wrong. Okay. Okay, so we understand the wave theory, right? And the important thing is wave is a surface wave, and the particle motion on the surface larger, and under the water surface becomes smaller and smaller. And then for the deep water, it looks like the particle round shape like that, and for the shallow water, this type of shape. Okay, so that is let's come back to this figure again, right? That give you sense what kind of wave look like, right? This particle, how quick is it decrease, and this is the shallow water. You can see this one. However, the ocean wave in the real life is not single frequency, right? It can be multiple different frequencies add together, and then let me make this hide. Okay, so this is regular wave, right? And if you add all this wave together, this is called irregular wave. The ocean condition is more like irregular wave. And in the next half an hour or a little bit more than half an hour, we are going to talk about the spectrum and use the spectrum concept to understand the irregular wave. Okay, so to understand that, we have to talk about random sea or random vibration first. Random vibration, for example, you record the wave amplitude, right? And then the wave amplitude and time series, and this is more random situation, random variable, random vibration, random excitation, whatever like that. So to evaluate that, here we need to introduce the concept of stationary. Stationary means and the statistics property wouldn't change over the time. That means, for example, you take average in this period time and in another period time is the same, this stationary. And this is for random variable, and it's hard to say exactly at this time what the amplitude it is. Therefore, we have to use statistic probability, this kind of concept, right? For example, the mean value, right? Mean value, you take this, integrate all this xt, and integrate time t long enough and divide by t. That is called mean value, right? This is time average. And another sense, mean square value, right? X square and integration you all the time given t longer enough. That's mean square value. So here they have root mean square, right? And you can have standard deviation is x minus the mean value square, right? This is sigma. Okay, so that's random variable. Okay, now what mean of spectrum? Before we introduce spectrum concept, we would like to introduce a correlation function. What's a correlation function? Okay, this is autocorrelation. What does that mean? You look like mathematically is x tau, xt plus tau. So the time together you do the integration. What does that mean? Okay, so your xt, right, you shift xt plus tau, right? Then you time the two variables together, right? Then you take time average. This is autocorrelation function R, right? So you integrate around the tau, eventually you get a function of t. right? This is the autocorrelation function. Just imagine that way you measure the time domain xt and you shift a little bit. After you shift that, you want this to say this is related or not, right? This is the autocorrelation function. So it's a function of t. Okay, so the physical meaning, right? Shift a little bit to say it's related or not. So then this will be function of t. Function of t, you take the Fourier transformation, you define that as a power spectrum, right? So here you already get this autocorrelation function, right? And you take a Fourier transformation. So then we call this spectrum. How to understand it? Well, let's give one case study actually to say what's the autocorrelation. I'm going to come back to this equation again later at the okay. Give some example. Okay, if you have singular, you have xt is harmonic, right? And is sine omega a times sine omega t harmonic, right? So then you take autocorrelation, shift a little bit, and you will find the autocorrelation and take this form, right? If this t equals 0, right? That means it's self, and it didn't shift at all. It's x squared, the mean value, right? Is here. You shift here a little bit to about quarter of this quarter of half pi. Okay, this is 2 pi. This pi. Okay, shift a little bit. This is half pi, right? Then autocorrelation function is 0. If you shift half pi, what mean? Is sine and cosine function. Sine and cosine function always perpendicular, right? Therefore, your time average will be 0. This autocorrelation function, right? And given this autocorrelation function, then you take Fourier transformation, you will get this in the frequency domain. You will have one frequency components only. What does it mean? So if sinusoid function here, there is only content one frequency, right? Therefore, in the frequency domain, you only show one frequency, right? That's called spectrum. Okay, so another thing is random excitation. Is your pure random signal, right? Is like that. And you shift this a little bit again, you get autocorrelation function. Autocorrelation function, this is a very interesting part. This is pure random, and if shift is 0, then that is x squared, right? You have some components. Then if shift is not, this tau shifting is not, t shifting is not 0, then the correlation function is 0. What does this mean? This means this is pure random excitation. This time and less time is not related. Therefore, if we shift a little bit time t, the autocorrelation function is 0. Right? Now, if you take this function and do the Fourier transformation in the frequency domain, you will find that the spectrum is flat. When spectrum is flat, what's it mean? It means the random excitation it has content of all the frequencies, right? All the frequencies contribute same. This is random signal. This is pure random, right? So pure random, the relationship correlation function is shift a little bit is not related, right? This is the autocorrelation function, and in the time domain in the space domain, look like that. All the frequency to have all the frequency component. Sometimes we call it white noise. Why is it called white noise? So Did someone say, Professor, this is a black and blue noise, right? You show blue color. Yeah, it cover all the frequencies, like white light. It has all the frequencies, right? This is called a white noise. You say there are some other definition. If you have spectrum like this one, is pink noise, because the pink color, the frequency domains like this one decay, right? So this is, I want to give you sense for the random excitation, how to understand the random variable in frequency domain, right? You have sinusoid component, you say one frequency only. Therefore, in spectrum, you say one frequency, right? Here is true random, like if you shift a little bit, then it's zero, it's not related. In time domain, in frequency domain, it contains all the frequencies. Okay. So for random system, and you put a buoy, whatever, in the water, right? It's one random excitation. We need to understand the input-output relationship. Okay, so for deterministic problem, like that way, you given the force, there's a displacement. For this vibration system, there's an input-output relationship. We call this as transfer function, right? And transfer function is in Laplace domain S, right? And you take S equal J omega, that is the frequency response, right? And this frequency response, you take inverse Laplace transformation or inverse Fourier transformation, that is called impulse response. We already understand that. This is amplitude. That is something we talk about in last lecture, and also at the beginning we record what the means of impulse response, right? That is deterministic problem, right? If you given arbitrary force input, you go through this convolution, you get the time domain response. And here, frequency domain or Laplace domain, you have input spectrum, time, the transfer function, and you get output, right? That deterministic problem, you get exactly solution. Now, how about random vibration? Random vibration and random variable at exact time, you don't know what's exactly, right? There's some spectrum. You need to use spectrum to understand the system, right? So for the given node, and this spectrum relationship is like that, okay? If you have transfer function h omega, okay, you have input spectrum, the output spectrum will be input spectrum time the transfer function square. And the transfer function is like that, amplitude is here, right? So therefore, and before I show you, I want to show you here, okay? Here, if your system, this is your input spectrum like that, then the transfer function takes this way, right? For this single diffraction system, you remember we have the quantity factor 1/2 zeta, right? The amplitude like that. So output spectrum is input spectrum times this square. Okay, therefore you can say output spectrum is the content, the input peak, right? And also frequency transfer function the peak. Okay, whether this dominate or this dominate, it depends on which one is larger, right? So now that is the input output relationship. And now come back to here again. So this is integration, okay, and the integration x square, okay, ex square, okay, what's ex square, okay, ex square, okay, let us go back to here again, and I skip one equation I can say here, okay, and mean square, ex square, right, integration x square like that way, right, that is itself is correlation function when t equals 0, right? Look at it here, right? the correlation function when t is 0. And now take a look at here. Okay, now when this is 0, now what's this part? 1. Therefore, this integration spectrum occurs all the frequency, that is root mean square, right? So here, this is why we just put this relationship here. So x squared mean value and this integration or the spectrum, right? This is input spectrum and transfer function. So like this region, you integrate the sigma square. Okay, sure, with this sigma square, assume this mean value is 0, right? So, okay. So, and you have many ways to measure the frequency response. You can say frequency response is important, right? And for example, you have vibration system, you can excite the system at a single frequency. 1 Hz, 2 Hz, whatever, you get at this point, link them together, get the frequency. Another, this will take a lot of time to do this type of single frequency measurement, right? You can have shaker swap sum, automatically you change 1 Hz, 2 Hz, right? You count all the swap function. This measure the frequency response. Another thing to measure frequency response, you do the time domain and you use hammer, whatever, to get impulse response first. Impulse response, you take Fourier transfer function, then you get the spectrum function, you get transfer function, right? And another way is this swap. I should acknowledge this figure I get from Google picture. I forgot who owned that. And anyway, I apologize. Someone says this. I didn't put the source here. Okay, so this impulse response also, and after you get the impulse response, you get Fourier transfer function. You get the transfer function in frequency domain. Another thing, you use shaker to get random excitation. Why random excitation? You get spectrum. The reason is random excitation, the input spectrum is flat, right? This is flat. Then after that you measure the output. You do the Fourier transform function itself is h omega square, right? You have different way to do the model test. Get the sense, the transfer function. Transfer function is very important to understand the system. Okay, and I skip this page. I already explained that. Okay, so now I want to tell you some relationship about correlation function and spectrum. You understand that this is one pair of Fourier transfer function. So, and this function RT, they call the correlation function Sx, is spectrum. RT is, you will find it's even function, okay? And so Sx here, that's even function. Another thing is spectrum is real value. That means there's no phase itself, right? A third thing, we already say that is sigma square. This integration of x squared t. This is also integration in frequency domain, integration in time domain, right? In such kind of thing, you can calculate the mean value in frequency domain directly. So since this is show that here the spectrum function is even function. Since it's even function, we have one concept we call single side spectrum. So, okay, so this double side spectrum, single side spectrum, just so positive side we have 2 sigma x, and negative side we take 0. We call the single side spectrum. Okay, so now if you are given this spectrum function, how to in the MATLAB simulation, how to generate time domain variable that can be representative of the spectrum function. Okay, and here we use that way. So you are given this continuous spectrum, right? And now in MATLAB you can have many sinusoid terms, add them together, and here we use this relationship. Time domain A is amplitude, omega gi is frequency at gi, and now use this relationship A. How large is A? Okay. And A is, you have spectrum here, Sx times delta omega, right? This is volume inside. Volume inside you have 2, the single side spectrum, right? So 2 Sx times omega and square root. So you can get now the amplitude here, right? So if you are given the spectrum like that, you can use time domain function generated. You can have multiple frequencies, add them together, and the amplitude here you can calculate using spectrum and the discrete of frequency, right? Now the amplitude is given. How about the phase? We say the spectrum is a real number, there's no phase information. So for this one, and you use a random phase, right? So that is how random phase, random number, whatever you generate from MATLAB, right? If you are given the spectrum from ocean wave, how to generate simulation in the time domain, that is the way you generate, right? The only thing is you take this spectrum discrete into small or delta omega, right? You have omega 1, omega 2, omega 3, omega 5, add all them together, you have A1, A2, A3, A1, A2, A3, you just use this way to calculate. Okay, then you can get time domain spectrum. So now we understand the spectrum autocorrelation function. Now it's time to understand the random say. And the random say you can just imagine that way. And you have wave come from different directions, right? Different amplitude, different phase. You add all this together. That is random say. Okay, and the random say people use spectrum to describe that, and same as other random variable. And to most common spectrum and is PM spectrum. Okay, first is for developed say, and for developed say that is means where the let me ask you, so far we talk about wave energy or common sense, where the wave from? Wind, right? So wave come from wind, right? Fully developed say means the wind below the ocean long enough generate steady status, right? And so that is a fully developed say. In fully developed say, the length should be long enough, right? This is known fetch. And in such kind of case, the spectrum will be function of the wind speed, right? And then it's a function of omega square, right? So then that is the PM spectrum, and that is curve fitting is not theoretical then so far, and curve fitting you can get this function. Okay, and different wind speed you have different spectrum, right? So at this frequency you have peak spectrum, right? So and here peak spectrum you know velocity, wind velocity, and you can calculate. Okay, so that is PM spectrum, and this is curve fitting from mirrored in North Atlantic Ocean, and it's fully developed sea. Okay, another spectrum, JONSWAP spectrum, and JONSWAP spectrum, this is mirrored in North Sea. You know where's North Sea? And is the UK side, right? And close to UK, and the North Sea. Okay, and that is not fully developed. That means the fetch distance is limited, right? And here is also function of wind speed, so plus some enhancement factor, right? So gamma and gamma 1, 2, and so how narrow it is. Okay, so that is also very popular spectrum people use for the wave energy converter design. Okay, so this is what means fetch distance. You have wind blow into the water, and then it generates wave, right? And this part, if fetch distance long enough, that is fully developed sea, and then this figure shows a comparison PM spectrum and JONSWAP spectrum, right? Keep in mind, and they have different is function of wind speed, and they have different application. One is a fully developed sea, and another is representative for the North Sea, not fully developed. So the real situation is like that. For example, in the Indian Ocean, you put a buoy there, you measure all the wave height, right? And this is amplitude. Amplitude, then you take this correlation function. After correlation function, you get a spectrum. This is real situation, most likely. Right, depends on location, they have different spectrum, right? So some of them, they have even two peaks like that. Okay, the spectrum again, and PM spectrum is measured in North Atlantic Ocean, is fully developed. JONSWAP is measured in North Sea, right? If you want to develop wave energy converter, put into Indian Ocean, the best you have such kind of measurement. Then you have your own spectrum function. Okay. So now I need to introduce some concept of significant wave height. Okay, and so wave height definition, right? You just imagine that way. You measure the wave amplitude like that way, and how to measure the wave height, right? And you say from here to here is one wave height, from this one is second, and from here is third, right? You measure all these wave heights. So then all this wave height, how to use that, right? So you record this data, you get all the wave height, and how to use that? This is you plot the number and wave height, right? You plot in that way, right? So it's more random number, right? Random number, okay. So is eventually it comes in like that. Okay, for example, and the wave height 2 meters, you get what's the percentage, right? So then you have 4 meters, what's the percentage? This is called power spectrum. No, this is probability density function, right? Probability density function, for most of that you can, anyway, for any kind of measurement you can get the probability density function. And one popular probability density function is Rayleigh distribution. Rayleigh function is take this form B and sigma square. Okay, so you can look more into Rayleigh distribution function like that. Okay, for Rayleigh distribution function, and it's you just imagine that way is the probability function of wave height. So the most probability wave function is here, right? So, and however, the mean value, if you take all this things, is not here, right? Is slightly higher. Okay, here the significant wave height, and let us define the significant wave height. Okay, so and this most popular one we call the mode, right? Significant wave height is 4 times sigma if follow Rayleigh distribution, and it doesn't need to be Rayleigh distribution. Any kind of recorded data like time domain, you can define significant wave height. So okay, significant wave height, and here is defined h 1/3. What the definition is, and the 1/3 of the highest wave height. Okay, so this is looks like confusing, and how to do this one? Just imagine that way. Now you record this, right? And just imagine that way you record this 1 meter, first one 3 meters, 6 meters, 3 meters, 2 meters, 9 meters, 6 meters, 5 meters, 4 meters, 9 numbers, right? 9 numbers was the top 3 numbers, right? Here the top 3 numbers, right? Top 1/3 of the numbers, right? Top 1/3 of number, look at this top 1/3, 9 is the largest, second largest is 6, a third largest 6, right? And top 1/3 of the number, add them together, you take average. This is 7 meters, right? This significant wave height is 7 meters, right? Don't think significant wave height is the mean value. It's quite larger than the mean value, right? And if you have Rayleigh distribution, mostly significant height is 4 times of the mean value. Okay, so and I don't know, Dr. Vijay's experiment will do such kind of significant wave height measurement or not. And you just generate a wave, random wave in the tank, right? You measure wave amplitude based on the measurement. Let us say you record one segment. During this segment, the top 1/3 of wave height, you take average. That is called significant wave height. Okay, significant wave height again is much larger than the mean value. If the wave height distribution follow Rayleigh distribution, like here, significant height is most popular. Okay, its mean value is here. Okay, the most popular happen is 4 times of that. Okay, mean value is square root pi divided by 2. Let us say that way, 3.1.7 square root 1.7. So it's 1.7 is okay. Look like 1.3. Okay, so it's for this one, it's about 3 times of mean value, right? And 4 times of most popular value. Okay, just time I try to calculate this square root pi divided by 2 divided by that, I say 3 times. Okay, so significant wave height is larger than typically like 3 times if Rayleigh distribution of mean value, 4 times or the most happened wave height. Okay, so now if you record some wave height in certain region, and there are joint distribution function. What's the joint distribution function? Okay, so this figure shows the energy period, right? Wave period, and another figure shows the wave height, significant wave height. Already learn how to calculate significant wave height, right? So, and this is joint distribution. Okay, let us take this one joint distribution. Let's take this number as an example. Okay, so among this wave period is 8 to 9 seconds, and the wave height is 1.5 to 2 meters. So this chance happen is 6.6 percentage. This is percentage of happen. What the chance to happen, right? 6.6%. And take this one is, for example, you have 60 meters extreme wave case, and it happened like 3.5 to 3 meters. The chance is 3%, right? So 0.03%. That is what the chance of the happen. This is joint distribution. This joint distribution function is very, very important. In this line, it shows the mean value of joint distribution function, right? And this line is 90%, this 5%, this percentage happen like that. And here, this is measurement. Okay. Another line I didn't draw. That is the equivalent. Along this line, that means the chance happen will be same. For example, here if I take 2%, what the chance 2% happen, right? You draw a line from here to here, you link them together 2%. Okay, so you draw a line 2% is more like that. Okay, this is one line and equal potential, equal. I forgot the name. Okay, what I mean, along this line, they happen same. Okay, so the chance happen will be same. Okay, this figure is very important. Usually, you record some measurement in the ocean and you produce this figure. And this figure you can use for all the energy calculation. This is percentage when it happen. I give you one example. So this is the result in our paper. Okay, we designed such kind of wave energy converter. In the first introduction, I told you, right? I have dual flap, right? Dual flap like that. And this dual flap we designed for pack wave side, and pack wave is DOE invest more than $100 million to develop a test site. It will be open soon. It's 15 miles offshore of Oregon State. Okay, so we would like to evaluate such kind of design. What the performance? The design, the flap is 12 meters, the height is 7 meters. The distance here we change. Some design we tried 45 meters, some design 55 meters, right? So for such kind of design, we want to put in the ocean, and we would like to see how much energy we can get. How to do the calculation, right? So this site, they give such kind of joint distribution function. This wave period, this wave height, right? And this number is how much power it have. Okay, so this absorbed power, basically, let me tell you what that means. We do that. We put this wave device into the water, and we do simulation and to look into hydrodynamics. For example, here like a 10 to 11 meters wave period, and if we say it's 4 meters wave, right? We put such kind of thing, harmonic system, and 10 to 11 meters of 10 to 11 meters wave period, and 4 to 4.5 meters wave height. You put in this situation, you generate this much of power, right? This kilowatts, 1,000 kilowatts. And however, this design and this is, we have to consider that the efficiency. You have generator efficiency. For example, here, if very slow speed generator, here you have 25 IT, and lower amplitude, you have lower speed, they assume the efficiency 25%. You higher speed, right, then you have higher efficiency, right? Another thing is for such kind of generator, and there's a generator capability. What does that mean? So if above a certain number, you control to protect the generator. For example, your generator is rated at 400 kilowatts, right? If your input is more than 400 kilowatts, you control the electric load of the generator to limit the power at 400 kilowatts. The same idea is used for the wind energy, right? Wind energy, you rated 5 megawatts when if we input whatever time is more than 5 megawatts, then you limit that, right? So after you calculate all this power with considering efficiency, okay, for example, here it's more than 400 kilowatts, then we limit 400 kilowatts. Okay, after we calculate all this power like that, and then we time the probability function, or they called percentage occurrence, right? Percentage occurrence times the power, then you can get how much power you generated over 1 year, right? And then eventually you can add all these cases together. You can say, my device, I put in this particular ocean, how much energy we can generate it over 1 year. Is this clear? And you have percentage, what kind of chance to happen, right? And you calculate all this power based on the hydrodynamics simulation, right? And now you have to consider realistic situation and efficiency or the generator's rated power, right? Then you get this number. The number time here, the percentage, then you get 1 year totally how much energy you can generate it. For this device, we estimate that if we deploy such kind of device in Pacquiao side, we can generate average 1 year is 100 kilowatts. This is how the 100 kilowatts is calculated, and we recently published in this paper. Okay, and the first author is a student, finished degree in Stevens Institute, and now she's postdoc in Cornell University. Second author was my student, and he finished degree with me, didn't go through the postdoc training, directly joined Stevens Institute as a assistant professor. Okay, for the details you can say this paper. Okay, so now I stop here. Overall, and today's lecture we talk about another sense, right? We just talk about impulse response to conclude the vibration situation. Then we quickly reviewed about the fluid dynamics. We understand what the streamline function, what the potential velocity potential, right? What the means of potential flow, right? And from that we come to the wave motion. Wave motion is solved, the equation solved beautifully with the potential flow plus a boundary condition. If you are graduate students, I encourage you to look into Newman's paper, understand that, and it's really beautiful function. Okay, they get I think 1846, around that time, I may be wrong, plus or minus some years. Around that time, people find the closed form solution. From the closed form solution of potential function, we can understand the potential flow, right? How the particle move at different speed, right? And what the pressure inside the water, right? And how the velocity change, and also the wave, there's the phase velocity, group velocity, right? And I already showed this, the phase velocity, group velocity, how it transferred. And after that, we talk about wave energy, right? Wave energy and is transferred at the group velocity, right? So, and from this wave energy, we already get a sense wave energy is a very significant large number and larger than the sonar. Now the question is how to get energy, right? And to understand how to get energy, we need to say the fluid structure interaction. So far we talk about fluid. We have not talked about fluid structure interaction yet. And tomorrow we are going to talk about fluid structure interaction. And in that sense, you will say some some number you may need some notation you may not hear about that. Added mass, radiation damping, excitation force, right? And after we understand this fluid structure interaction, we can understand the wave energy converter modeling. And if you understand the dynamics, you have designed something, you can have better sense how to improve the design. Okay, so next lecture we are going to talk about wave structure interaction. Then we talk about frequency domain modeling, time domain modeling, right? Then from frequency domain, time domain modeling, you come back again, become vibration certain how much energy you can get from the wave energy converter. And after that, we talk about PTO design, VEC design side, right? So hydrofluid itself is very important, but it's not enough. We have to put everything in a tank in the open water to make the work. Okay, so I stop here. Any questions? Again, I will, after the class, I will stay here for half an hour and then we can chat. Okay, so after half an hour, I have to go to the guest house to get a lunch. The lunch closes 2 p.m. and after 2 p.m. and I can come back to here to take a look at the graduate students' work to see what's going on in the lab. So, yeah. Okay, question?
So thank you so much, Professor. I just want to say one thing because I did my master in the same area and the PhD. So last 4 years, I had done multiple courses related to wave hydrodynamics, coastal engineering, all these things, floating bodies dynamics. So
you understand the topic very well.
Yeah, so within this last 3 hours, it was a whole kind of recap of everything, and I learned, and now I realize practically how things works, right? So thank you so much. My question is, as you said, the Aqua or the VAMIT, right, or any BM tool, this is based on the potential theory, and they assume a linearity in the system.
Yeah.
But generally, when we put our wave energy converter or something in a fluid, so it has got viscous effect in practical sense, and it has multiple non-linearity in the system. So is there any way after doing the potential theory analysis we can incorporate in that system, or we can?
Okay. He pointed out a very good question. Okay, and all the wave energy converter, not all, most of the paper you look into that, the calculation simulation are based on the potential flow. Potential flow, there's an assumption. Assumption is the amplitude is small, right? And where wave energy converter, many times the amplitude is pretty large. So after all this potential flow calculation design, you have come back to check, use high fidelity code to see how good your result is, right? And the potential flow is used for the quick design, quick iteration, right? But after that quick design, quick iteration, you need to do high fidelity calculation to consider the viscosity effect, to consider vortex or the shape like that, right? And all this high fidelity modeling, let us say for our case, like this design, if you use ANSYS Fluent to do the calculation, one calculation take 1 month, right? 1 month, you run that 1 month later, you get some result. Wow, I get screw up. I forgot this number. I get some dimension wrong. You run another 1 month, right? Or I say, wow, all the dimensions right now. I just wondered if I change the dimension instead of 55 meters. I want to say, how sensitive to this distance change, right? At 55 meters, I assume is half wavelength. Now, 55 meters is too long. I don't want to pay the cost. I want to reduce to 35 meters, right? You need to calculate another 1 month, right? It takes a lot of time to do the calculation. It's not good for the design, and it's good for the validation. It's a combination. Therefore, and recently we published another paper we called multi-fidelity and iteration process, right, to design the system. Okay, thank you.
Thank you so much, sir.
Yeah.
Anyone? Okay, sir, I have a doubt. Sir, you told the significant wave height, you told 1/3. Why 1/3?
Say it again, significant wave height.
No, sir, you said the calculation, instead of mean, we calculate significant.
Yeah.
That is 1/3.
Yeah, 1/3.
Why 1/3?
Why we use that, right? I don't know why, honestly. Why not we use mean or mean square, right? And we always like this power matrix. Sometimes we just call power matrix wave period and significant wave height, right? Do you know why we define it in that way? Do you know why we define that way? I don't know.
Sometimes they consider 1/10 also, right?
Yeah, consider 1/10 here, right? It's 1/3, 1/10. Yeah.
I think it has come from the experience. They have seen a lot of that.
You say this figure, you can get sense, right? Significant wave height, this is 1/3, and this highest 1/10 of wave, right? Yeah.
Thank you.
Okay.
Anyone else? I want someone has to ask, not others, not our own people are always asking. Okay. Professor, actually I have one query.
Yeah.
Like in an impulse response function, that convolution term, no, that generally people are doing with numerical integration. And that you mentioned that some exact method is there using some Laplace method or something like some exact solution is there for solving the convolution term. When I am going to apply it in my wave energy, so I have to use for radiation damping, I have to apply that whatever I run in the
right,
I am using convolution term that in the time term. So is that either way to I'm using in numerical method to solve that? So numerical integration.
And
so
you mean Cummings equation like that?
Correct,
yeah.
Exactly. So
okay.
I want to solve in an analytical way to get the solution for convolution term.
Yeah.
So is there any analytical way is there to solve?
And you talk about radiation damping term.
Correct.
Radiation damping term for the simple shape is just a closed form solution.
Correct.
Right? And for general case, is numerical solution.
Yeah.
And after numerical solution, you get impulse response. You can use state space to calculate it quickly. You normally fourth order and second order state space is good enough for many applications. So, and actually, this is why I come back to talk about the impulse response again. And when we talk about fluid structure interaction, we have to talk about Cummings equation, that part, radiation damping again.
Okay.
Yeah.
Thank you. Anyone else, please? at least someone, the participants.
So overall, is let me say that way. Quite a few students are sophomore. Don't get too scared like that. It's okay. And I need you say what's going on, right? Although mathematically I skip that part. This is for this reason. I don't want you guys get overwhelmed by all the derivative of the equation. But I encourage the students, especially graduate students, look into how this closed form solution about velocity potential, this type of equation, how we get that, yeah. Okay.
So previously you have mentioned about the standing wave generated due to the reflection of the waves. So near ports and harbors, we construct the breakwaters to minimize the standing wave to reduce the impact on the ships.
Yeah.
Can we maximize the standing wave to capture the heave response through the wave energy converter?
Yes. For wave energy converter, sometimes we do such kind of hydrodynamics to increase the power output, right? So you standing wave, some wave you have guide and magnify the wave amplitude. Yeah, this is a good idea. Okay, thank you.
Anyone else?
Last question.
The last question, please.
You guys are all okay? This is fine. Okay. And just relax on it a bit, as I said, if you have some research ideas, some questions, and feel free to bring up for the discussion, right, in one-to-one meeting, whatever like that. When I teach course, I normally ask students to look into some research question, research problem, use the knowledge they learned in the class, right? In this course, Dr. VK and Professor Summit, we are going to give you some experience in the tank. And if you have some research idea, we can discuss more. When I was a student, I published 2 papers from my coursework. So I just take the course, I have some ideas. After the course, I continue to discuss with the professors and write the proposal, write the paper with them. Yeah. Okay, let us stop here. Yeah.
Professor, regarding the question of significant wave height, the why 1 by 3, right?
Yeah.
Yeah. I could recall the discussion that when we were students. To the best of us, it was like in the couple of years back. Couple of decades back, when there was no defined instruments to measure the wave heights. So at that time, people it's all about the visual documentations basically. So in much of the sites, when they documented based on the visual observations, the wave height, whatever they have recorded, okay, at a distant ship, like from here we recorded. So when they started getting the sophisticated instruments to compare them, they were able to get closer with the significant values. So that is the reason why 1/3. Basically, when they were able to measure wave height at that particular site, and they were able to get the top high 1/3, and that is able to have a good match. So whatever people were able to see, that had a significant match with the significant wave height. So
that is more like a feeling, right? You look into the ocean like that, you get sense.
Yes.
What
so,
height,
yeah,
right?
So that's
okay.
Yeah.
Okay.
I was just wondering this question, then able to slowly recall what was the explanation given to us when we were at that time questioning this.
Okay, sure.
Yeah.
Right. Okay, it's good. Okay, let us stop here.